The history of the Parkgate Company dates back over 140 years. The works were founded in 1823, producing iron and iron castings, but since 1888, steel has been the major product. Throughout its history, the company's products have acquired a high reputation for quality, and no effort has been spared to maintain this reputation. The willingness to apply technological change has played no mean part in this, and the works have developed progressively over the years. The reputation of Parkgate quality steels has spread throughout the world. The most important step forward in recent years was the building of the 11-inch continuous bar mill commissioned in 1953. This modern high-production mill rolls steel bars of the highest quality. A feature of the mill is the rolling of coiled bar. The 6th of July 1964 was the greatest day in Parkgate's history, for on that day the major development of the works was officially opened by Miss C.H.T. Williams, wife of the chairman. This day represented the culmination of years of planning and design studies initiated in 1956 when Parkgate became a member of Tube Investments Limited. A large gathering of distinguished visitors were present at the opening to see the works which had taken just less than 3 years to build. One of its main features is the new steelmaking department based on a combination of oxygen and electric arc steelmaking. The Caldo oxygen steelmaking process was chosen by Parkgate for its flexibility and control. This process, which originated in Sweden, produces steel from molten iron and scrap. The electric arc furnace, chosen specially to extend the company's range of alloy and other high-grade steels, is alongside the two Caldo furnaces. Hot steel ingots are rolled in the primary mill to produce the blooms, billets and slabs used in the existing bar mills and the narrow strip mill. The installation of the strip mill represented a new product for Parkgate. The mill was designed around the strip requirements of the TI group. The administrative staff are housed in a new office building, which also contains the central computer installation. Three linked computers assist production planning and control for the entire works. One of these is online in the primary mill to ensure maximum yield and efficiency. A fourth computer was added to provide a more extensive production planning service and to undertake payroll, accounting and statistical work. The scheme was inaugurated on the 24th of February 1961 by Lord Plowden, chairman of Tube Investments Limited. As the first sod was cut, so the giant scrapers rolled into action, commencing the vast civil engineering program with the clearing and levelling of the site. In 7 months, over 4.25 million cubic yards of earth were to be moved. Some of this work involved blasting hard rock, which, after breaking up, was transferred for use as fill for the lower ground. To allow site transport to move freely, over 6 miles of roadway was constructed as quickly as possible. Free movement between the development sites was prevented by the River Don, running between the Thryber and Aldwalk sites, and 2 sets of mainline railways separating the Aldwalk site from Roundwood. Temporary bridges were built, and these were soon in constant use by the excavating and earth-moving traffic. As access between the sites would be necessary when the new plant was operating, the temporary bridges had to be replaced by permanent structures. A start was made on these towards the end of 1961. The building of the bridge over the mainline railways posed access problems. Possession of the railway was granted for 24 hours on New Year's Eve 1961. At that time, in spite of appalling weather conditions, the temperature was well below zero, the main beams were placed in position. By early 1962, site preparation was complete. and the final stages of civil engineering commenced with the laying of the building and plant foundations. As the buildings began to take shape, the first impression of their size was gained. Over 10,000 tons of steel went into the structure of the new primary mill building, and some 100,000 cubic yards of concrete were laid for foundations. As the civil engineering program progressed, manufacture of the plant and equipment to be installed was proceeding in suppliers' works up and down the country. The assembly of the flying shear at Bedford, the Bloom Mill at Sheffield, and the Caldo furnaces at Thornaby. All this plant was soon to be on its way to Parkgate, for as soon as the buildings were completed and some shelter from the elements afforded, so plant installation proceeded. The new plant could not become operational until the essential steelwork services had been installed. All the electrical power required throughout the plant is distributed from this central control room. 2 miles of insulated pipe supply steam from the boiler installation at Parkgate. Probably the most essential service required for the Caldo furnaces is the supply of huge quantities of oxygen. A plant capable of producing 150 tons per day was installed to meet this demand and to supply the rest of the works. Storage tanks were installed to act as reservoirs and to smooth supply. Some idea of the importance of water supplies can be gained by the volume of water circulating throughout the plant, approximately 1 million gallons per hour. Water is extracted for make-up purposes from the River Don at the rate of 80,000 gallons per hour, and this first undergoes extensive treatment. A great deal of attention was paid not only to the efficiency, but to the appearance of the lighting system. A total of some 700 lighting standards were erected to light the roads, railways and sidings. Travelling with molten iron from the blast furnaces at the existing works, the diesel locomotive provides the initial production link with the new plant. The iron is transferred to the new steel plant for use in the Caldo furnaces. The molten iron is stored in an 800-ton hot metal mixer furnace. Hot metal is taken by transfer ladle from the mixer furnace and poured into the Caldo furnace in its charging position. One of the main assets of the Caldo furnace is its ability to melt large quantities of scrap. The scrap is charged from large capacity pans. The vessel is swung into the upright position and lime for slag making is poured in from the high-level storage bunkers. The vessel is tilted into its inclined operating position, the fume exhaust hood swung into place and the vessel rotated. Oxygen is then blown in at a predetermined rate. The oxygen removes the silicon, manganese, carbon and phosphorus impurities and raises the metal temperature. When the calculated amount of oxygen has been blown, the blast is turned off and the hood swung aside. All operations are controlled from a pulpit alongside the furnace. As this was the first Caldo plant to go into production in this country, it was necessary to retrain even experienced steel plant operatives in the new techniques. This retraining included individual instruction on specially designed mimic control panels, as well as periods of training at the Domnarvet works in Sweden. More lime is added and the oxygen blowing continued. After deslagging, a metal sample is taken for analysis and the temperature checked. The metal sample is placed in the high-speed pneumatic tube system which conveys it to the technical center. The sample is received in the sample preparation room. Without delay, the sample is prepared and the technician places it in the Polyvac 1220 spectrometer. The rapid analysis technique was provided to meet the demands of oxygen steelmaking. Coordinated analytical services allow control at all stages of manufacture. A special feature of the Polyvac installation is a general-purpose analog computer for direct conversion to percentage element and automatic recording. A copy of the report is sent back to the steelmakers without delay, and they have all the information required within a few minutes of dispatching the sample. Back at the Caldo, a final temperature check is made, and once the correct conditions have been established, the metal is tapped into the waiting ladle. Over 90 tons of high-grade steel are produced at each cast, and the production cycle can be complete in just over an hour. The deoxidation and alloy additions are made to the metal stream during tapping. The molten steel is teamed into ingot molds carried on casting cars before transfer to the stripping bay. Alongside the Caldo furnaces is the electric arc furnace, which melts 100% scrap charges, producing high-quality alloy steels. The roof of the furnace is lifted, and the scrap is then charged from a basket carried by overhead crane. The furnace roof is swung back into position, the electrodes lowered, and the power switched on. All operations are centrally controlled from the nearby pulpit. Slag making additions are charged by means of a mobile charging machine. The furnace is slagged off, an operation which is repeated several times. The furnace is equipped with an induction stirrer which aids this operation and ensures uniform bath conditions. In addition to all the modern technical aids, a great deal depends on the skill and experience of the men operating the furnace. When ready for tapping, the furnace is tilted and the cast of over 90 tons of steel poured into the waiting ladle. The production cycle usually takes about 5 hours to complete. The steel, now in solid ingot form, is transferred hot in specially designed insulated road trailers to the primary mill. Ingots which are not to be rolled at once are transferred to the ingot stockyard. Before rolling, ingots are heated to a working temperature in reheating furnaces. After withdrawal from these furnaces, the ingots are transferred into the mill on a bogie, the position of which is automatically controlled. The ingot is first weighed and then moved onto the mill ingoing roller table, which conveys it to the bloom mill rolls. The reversing bloom mill incorporates all the latest developments in rolling techniques and is capable of rolling up to 20,000 tons per week. Rolling is controlled by programming equipment which automatically controls roll and roller table reversals, screw down and manipulator position. Only the tilting operation is controlled manually. The ingot is progressively reduced in cross-section during rolling, and the resulting bloom is passed along the outgoing roller tables to the continuous hot scarfing machine. For exacting surface quality requirements, the four surfaces of the hot bloom are scarfed simultaneously by means of sets of oxypropane gas burners. The surface metal is removed to a controlled depth up to 1/8 of an inch. The bloom passes to the 900-ton shear. Bloom lengths are measured on the electrically operated stop and measuring gear with the help of closed-circuit television. After shearing, any blooms not proceeding to the continuous billet mill for further rolling are transferred to the bloom storage bay. Blooms for further rolling into billets or slabs pass to the continuous billet mill. In this mill, there are a series of 6 stands through which the material passes in a continuous sequence, with its cross-section being progressively reduced to the required size of billet or slab. The stands are arranged in 2 groups, a roughing train and a finishing train, which are separated by an intermediate roller table. After leaving the last finishing stand, the billets are cut to length by the flying shear, which is controlled by an online computer to provide optimum yield. It shears any desired length from 15 to 32 feet and operates at a delivery speed of up to 750 feet per minute. The finished billets are directed to a double-sided skew table where they are batched and transferred to a position opposite one of the cooling beds. The billets are skidded across the beds into the billet finishing bay. This bay is used for the inspection and dressing of the steel billets. Shot blasting facilities are provided as an aid to surface inspection. Cold sawing and shearing facilities are available to provide billets of any specified length. provides one of the final stages in processing the steel made within these works. It produces strip from 3 to 10-inch width and 2 to 20-gauge thickness. A great deal of the output of approximately 3,000 tons per week is supplied to the Tube Investments Group. The slabs or billets produced at the primary mill are passed through the reheating furnace and arrive at the discharge end at the correct temperature for rolling. The slabs are discharged onto the transfer table, from which they are moved across to the mill approach table. These operations are all controlled from an adjacent pulpit. The front end of the slab is cropped by the pendulum shear before it enters the mill train. The roughing train consists of 6 roughing stands and 2 vertical edgers. After passing through this section of the mill, the initial thickness is reduced to between 0.3 and 0.5 of an inch, depending on the finished gauge of strip required. The front end of the strip is cropped by the flying crop and cobble shear to ensure proper entry to the finishing section of the mill. The strip then passes to the 6-stand finishing train. To achieve accurate tolerances on the thinner gauges, the last 5 stands of the finishing train are of the 4-high type. All rolling operations are controlled from the main mill pulpit. The mill is equipped with width and thickness gauges for automatic measurement and recording of the dimensions of the rolled strip. After going through the last finishing stand, the strip passes to the twist guides, which turn it on edge and direct it onto one of the 2 apron conveyors. The vibrators cause the strip, which is moving at very high speed, to snake out onto the apron conveyor. The apron conveyor carries the strip to one of the 2 vertical coilers. A cross conveyor transfers the coil. Coil inspection units are provided to ensure a high standard of surface finish. The maintenance facilities for the new plant integrated as far as possible with existing departments. An additional engineering workshop was built to carry out maintenance functions as well as storing essential spares. To satisfy the increased demand for craftsmen, the intake of apprentices was increased and a specialized training workshop provided. The additional labor to operate the plant required the recruitment of around 1,300 people, bringing the total number of staff and operatives to over 6,000. To cope with the increased number of technical and staff trainees, the company's education and training facilities were expanded. As an extension to their academic training, the trainees received special instruction on the new plant and techniques employed. Means of control. The guiding principle in design and in the choice of processes and plant was to enhance Parkgate's reputation as a maker and supplier of quality steels. The layout of the plant provides for ready expansion of all facilities and for the organization to be even further developed over the years. With the completion of this major development program, Parkgate looks forward with confidence to a high level of performance and service to its customers.